So let's talk about some applications of series circuits. And first, let's work through an actual design problem using everything we've learned about series circuits. For instance, let's say we're told that we need a circuit with 3 series resistors such that R2, the voltage drop across R2 right here is 3 times more than the voltage drop across R1, and the voltage drop across R3 is 4 times the voltage drop across R2. How would we find the resistor values that would make that happen? So let's work on this design circuit. We were asked to find R1, R2, and R3 so that V2 is 3 times V1. Let's put R V1, and V3 is 4 times V2. All right, so what does that even mean? Okay, so that means if this voltage drop is V1, then this voltage drop should be V2, and this drop would be V3, right? Well, if V2 is 3 times V1, then I'm just going to substitute that right up here and say, well, that's just 3V1. And then V3 is 4V2, right? So if I substitute that, that's fine, except V2 is 3 times V1. So I'm just going to take my V2 back and make that 3V1. So now, remember, my Kirchhoff's voltage law equation has to be upheld, and I've got just one variable now. So that would be a plus 64. I don't know why I wrote 16. It's plus 64. Traveling around this way. Minus V1 minus 3V1 minus 4 times 3V1, which is 12V1, and equals 0. So this is what has to happen in our circuit. So when I work on this a little bit, I've got, I'm going to combine my V1 terms. So I have 64 minus 16 V1 equals 0. When I move the V1 over to the other side, it becomes positive. And now I'm going to divide both sides by 16. And that tells me that V1 must be 4 volts. Okay, fairly simple there. Well, it requires a little bit of algebra, so you might need to brush up on your algebra there. So V1 would be 4 volts, and then we said V2 has to be 3 times that. So that would be 12 volts. And then V3 would have to be 4 times that, which is 48 volts. Okay, just using these equations. So how do I find my resistor values? Okay, I know the current through all of them is 10 milliamps. So I'm just going to use Ohm's law now. So R1 would be V1 over I1, where V1 has to be 4 volts and I1 is 10 milliamps. So that would be 400 ohms. R2 is V2 over I2. We found that that would have to be 12 volts divided by the 10 milliamps. And that would be 1.2 kilo ohms. And R3 would be V3 over I3, or 48 volts over 10 milliamps, or 4.8 kilo ohms. So those are the resistor values that would make this design work the way we were told to make it work. So we've got 4.8 kilo ohms there. So now let's talk about some applications. We have learned that we've learned a lot about series circuits. The current is the same throughout the circuit, and you'll have different voltage drops across the elements. But let's talk about a couple of key points here. First of all, if one element in a series configuration should fail, it's going to disrupt the response of all of the series elements in the circuit. And if an open circuit occurs, that means the current is going to be zero throughout the circuit. Nothing will work. However, if we have a short circuit and we actually short out one of those components, the voltage will increase across the other elements, and the current's going to increase in total magnitude as well. So also we need to keep in mind that for the same voltage, the more elements you place in series, the less the current and the less the voltage across all the elements in the series. So because as you add elements in series, remember we're increasing the resistance when that happens. So the current's going to be the same through each element of a series combination, but the voltage across each element is a function of the resistance of that particular component. Okay, so keep those things in mind. Now, it's easy to see why it might not be a great thing to have a series circuit, right? If one thing fails, everything fails. That sounds really bad. However, there are some really good uses for that. For instance, let's say you have some kind of system where you need a certain number of things in place before full power is applied. For instance, let's say you've got a conveyor belt and you want to turn that on and it moves really fast, and that's great. But you want to make sure there are some safety features involved, like maybe that there's nothing blocking the conveyor belt, or that there's not a person standing too close to the conveyor belt. Maybe these are things you check for before you start it, so that when you push that button, if those things are not checked off the list, so to speak, that conveyor belt does not start. So that's a good place to use a series configuration of a circuit. You're probably all familiar with some holiday lights that have a series connection between the bulbs. And what happens is when one bulb fails, the entire strand goes out, and you have to actually look through those. There are some other ways of building out the bulbs so that that doesn't always happen. And that is the basis also between for the flasher type lights. Let's look at a microwave oven. This is another place where the series configuration is actually helpful. We have a number of safety switches which make sure that that seal on that microwave is good before we actually turn it on and create those microwaves through the box. So if any of them is not working properly, your microwave won't come on, and that's actually probably a good thing. Let's say you have an alarm system in your home. You want to make sure the door is closed, and when it's not closed, you want an alarm to sound. Again, that would be a series connection between all of the different factors, so that you find that if any one of them fails, you get that alarm in your circuit. And those are just some of the applications of series circuits. They can actually be a really good thing, depending on what your application is.